And I'll start soon. So now we're recording it again. So we have these intervals. And sometimes I'll forget. Eventually I'll post these recordings on probably the YouTube. I'll make a YouTube link for you. And then just like the multivariable calculus one, there will be one that says map 215, and it'll just be these live lectures. And I'll label what they are in each one. So in each of these, we have an xi minus 1 star and an xi star interval. And the length of each of those intervals is what we call delta x. And that delta x is b minus a over n. So we're chopping up the interval ab into n equal parts. So each of the subintervals length is, or the width of this is equal to delta x. That delta x is always b minus a over n. And then we get, with the right-hand endpoints, the xi star is picked to be a plus delta x times I, which is a plus b minus a over n times I. So these are, and then f of xi star is equal to f of a plus b minus a I over n. So what this is, the width of the rectangle. What this is the height of the rectangle, f of xi star. This is the height. So what's the area of one of the rectangles? If I call this area I, say, then I'm going to have area I is equal to length times width, which is equal to, in this case, f of xi star times delta x, they say. And then what's the area under f of x? The graph, technically, but I'm lazy. Under the graph of f of x, above the x-axis, which is actually y equals 0, and between the sides, x equals a and y, x equals b, two vertical lines. So we have this total area that we want to compute. Under f of x, above y equals 0, and between x equals a and x equals b, y equals 0, and y equals the graph of f of x. So we basically have a box, but the top is saggy. So what is this area? Is approximately, first, what is this approximately? The area under f from a to b is approximately equal to, they tell us, the sum from I equals 1 to n of the AIs, each of those areas of those rectangles. And that's going to be the sum from I equals 1 to n of f of xi star times delta x. So that horrible sum in the Riemann sums, the reason I'm doing this is because we're going to do this in 2 and 3 dimensions right away. So it's not going to get better. It's going to get double sums, etc., etc. So what we're going to do now is to get the exact limit, or the exact area, we take the limit of this and we chop it up finer and finer. And what that does is essentially push n to infinity. exact area under f of x above the x-axis between x equals a and x equals b is the definite integral of f of x from a to b. And this is denoted by the symbol integral from a to b of f of x dx is by definition a limit as n approaches infinity of the sum from I equals 1 to n of f of xi star times delta x. This is the definite integral. And coincidentally, if you have a positive function, it's the area. Area under f of x above the x-axis between those two values. So this thing, total area A, is what we want. Why do we point this out? Because it might be a while since you've done this also, but now what we're going to do is we're going to do this in more than one dimension. We're going to do it in 2 dimensions, and then we're going to chop up. First, we're going to now chop up, instead of just chopping up the interval AB, the one-dimensional interval, now we're going to have a rectangle, and we're going to chop it up horizontally and vertically. And then we're going to have a cube eventually, and then we're going to have a cube as our domain, and we're going to chop it up horizontally, vertically, and linearly, or in rows, columns, and aisles. We're going to have to chop it up 3 ways, and then we're going to get the triple integral from this. But first, now we're going to do double integrals. And as an example, if you're going to compute the integral from 0 to 1 of x squared dx, or x squared plus 1 dx, you can either use 1 Riemann sums or 2, you can use fundamental theorem calculus. Part 2. And so doing this, what do I get? You're going to have to remember that you're going to be expected to know a lot of integration, especially definite integrals, because this isn't going to get better in some sense. It's going to get much worse. Well, once we have triple integrals or higher than this, you're having to integrate the variable x and the variable y and the variable z. And so you have to do these definite integrals or indefinite integrals 3 times with respect to x and y and z, and then you have to carry some other variables constant at some point. So this was going to get out of hand real fast. So this is not an entire waste of time doing this integral by definition. The Riemann sums is a little bit of a waste of time maybe, because you're not going to have to do this, but it's the definition that I'm going to extend to 2 dimensions. So 1, if I'm using Riemann sums, I know that my interval is 0, 1 is my interval AB. So delta x is b minus a over n is just 1 over n, 1 minus 0. I also know that xi star using right-hand endpoints is a plus delta x times I. So that should be 0 plus I over n, which is just I over n. I need that to compute f of xi star, the height of my rectangle. So that will be f of I over n, which will be I squared over n squared plus 1. Now finally, for the area of a rectangle, I need f of xi star times delta x. This is I squared over n squared plus 1 times 1 over n, which is I squared over n cubed plus 1 over n. At this stage, the degree of I should be 1 less than the degree of n in each case, in each term. Then what are we going to do? This says that the integral from 0 to 1 of f of x dx, which in our case is x squared plus 1, is equal to, by definition, the limit as n approaches infinity of the sum from I equals 1 to n of f of xi star times delta x, but I already computed that. That's I squared over n cubed plus 1 over n. Now what I do is I distribute the sums of i's. This becomes the limit as n approaches infinity of 1 over n cubed, the sum from I equals 1 to n of I squared plus 1 over n, the sum from I equals 1 to n of 1. Which is, now I put the sums of i's, the closed forms for these, into the expression for n's. This gives me the limit as n approaches infinity of 1 over n cubed n plus 1 to n plus 1 over 6 plus 1 over n times n. Once I do that, I can write this as 1 over 6, the limit as n approaches infinity of n over n plus 1 over n, 2n plus 1 over n plus 1, which becomes cancel, cancel. Now I'm going to push the n through on the bottom. This is 1 over 6, the limit as n approaches infinity of 1 plus 1 over n, 2 plus 1 over n, and then plus 1. Why am I doing this? Because the reciprocals always go to 0. 1 over n goes to 0 as n goes to infinity. So this is 1 over 6 times 1 plus 0 times 2 plus 0 plus 1, which is 2 over 3. No. We have 2 over 6, so 1/3 plus 1, which is 4/3. So what we're doing here is we're computing the area from 0 to 1. We're computing this thing from x equals 0 to x equals 1. And that is the area from 0 to 1 of x squared plus 1. This is what we're talking about. This is the Riemann integral. Or what we're going to now use in this class systematically is what? We want to use the fundamental theorem of calculus part 2. And we're going to get the fundamental theorem of calculus part 2 implies the integral from 0 to 1 of x squared plus 1 dx is equal to the antiderivative 1 over 3 x cubed plus x evaluated from 0 to 1, which is equal to 1 over 3 1 cubed plus 1 minus 1 over 3 0 cubed plus 0, which is equal to 1/3 plus 1, which is 4/3, much faster. But the reason I point this out is the Riemann sums are exactly what we're going to use in a second for extending this to double integrals. And the fundamental theorem of calculus part 2 is how you're going to want to compute iterated integrals in general. You want to find the antiderivative and then compute using f of b minus f of a. So now we want to extend this idea of Riemann sums. to double integrals over rectangles. All right, so now I have to draw a picture in 3 dimensions, but I won't get too crazy if you don't get too crazy when if you don't make me draw too crazy of things, I won't make you draw too crazy of things on exams, etc. But now what we're going to have is like this. So here's the x-axis and the y-axis. And so now what we're going to have is we're still going to have, say, from A to B. But then now we're also going to have a C to D. Say somewhere out here. So that's going to be our rectangular domain. That's good. And then what we're going to do is we're going to chop up using m equal parts and n equal parts. Now we're just going to chop up both directions. Possibly not the same. We'll use an m, so we're going to get a delta y in this direction and a delta x in this direction in each case. And then what we're going to have is we're going to have some surface. It's hard to draw. We're going to have some surface S. Okay. And what we're going to do is, I should draw this a little bit smaller. Sorry, just a second. Didn't work. Strangely, it has to be here. This is how you draw it in 3 dimensions, like this. It's supposed to be coming down. So what you're supposed to get is the back face of this. So what we get is the surface, and then directly below that there's a rectangle now. And so now what we're going to get is we want to have the volume of this integral over the rectangle. So what we're going to do is, first of all, what we're going to do is this. Now I have x and y, and I have z is a function of both x and y now. Now we're doing 2-dimensional functions, or functions of 2 variables. Once I have that, now we have, just like I was saying in the picture, we have an A to B in the x-axis, and then now we have a C to D, say, in the y direction. We're going to chop up and create a rectangle and do double Riemann sums, essentially. And so in the vertical direction, we can chop it, and in the horizontal, we can chop it. Now, once we chop that up, we're going to get still the same thing, delta x's, and then now this time over here, we're going to get a delta y. Delta y is going to be d minus c over m. Delta x is going to be b minus a over n. You're going to pick sample points. So this is going to be xi star, let's call this a j, yj star, are sample points in each subrectangle. Aij this time. Just one rectangle is Aij. subrectangle Aij. So just like we did it in each sub-interval, when we chopped up the interval into pieces, what we had to do was we want a sample point in each one. We just pick right-hand endpoints. So we might pick right corner endpoints. It doesn't really matter, but we're picking some sample point inside the rectangle. There's a whole lot of points we can pick, but usually they're going to pick the bottom left corner, etc. And then you would just pick that for each one. Each rectangle would have these guys. And then same with the rectangle below it. Same with the rectangle below that and above. So if I was picking bottom right corners as my sample points of each rectangle, that's what I would pick. And then what does that do for us? That gives us, we now know that the area is equal to length times width again, which is going to be, we can call that delta A. The area of that guy is going to be, which we can call length times width, which is going to be delta xi star times, delta, I don't need the I in there, sorry. This will be delta x times delta y in each case because we make the subintervals the same, and we're just going to call that delta A. And now, so the volume under the surface f of x, y in that subrectangle, above that subrectangle, is equal to length times width times height now. So the volume of that subrectangle now, because we have the surface above that, we have a subrectangle. AI, and that has delta A as its area. But now above that, we have the surface portion. So that should be the dashed one. So now if we have that box, but now it's got this little surface piece on there, the volume of that is going to be exactly equal to length times width times height, which is going to be f of xi star yj star, my sample point, f evaluated at that sample point, times delta A, or vi is equal to f of xi star yj star times delta x delta y in Cartesian. Delta A is going to be the Cartesian area differential. What we're going to do eventually is polar and cylindrical and spherical coordinates, and when we change coordinates or change variables, this area differential changes slightly as well, but we'll get into that later. So now, what do we have? The total volume V under f of xy, the graph or the surface now of f of xy, above the rectangle. What's the rectangle now? We're going to call it R, and that's going to be AB Cartesian product, so cross CD is what they call it, is approximately equal to volume is approximately, not exactly yet. So we're developing it exactly the same we did the one-dimensional Riemann sum. Instead of chopping up the line, we chop up a rectangle into two directions, and then at each subrectangle we pick a sample point. Above that we get an approximate volume, and then we add all of those volumes up. So we're going to get this is equal to the sum from I equals 1 to n, the sum from j equals 1 to m of f of x I star y j star delta x delta y, or delta a if you want to be lazy, but I like to leave the differential because we're going to change it later. That's the approximate volume. And of course we're assuming f of x is a positive function. So that just like in the one-dimensional case, if our surface doesn't dip below the positive part of the real 3 space, then we can compute this as volume, just like in the picture that I drew. So we're trying to compute this volume. This is the volume V. So what is the exact volume going to be? We're going to chop it up finer and finer, and then we will get exactly the volume. So definition, the double integral of f of x, y over the rectangle R equals AB cross CD is defined as the double integral over the rectangle R f of x, y dA is equal to the limit as m and n approach infinity of the sum from I equals 1 to n and the sum from j equals 1 to m of f of x I star y j star delta a or delta x delta y. But this is the precise definition. Well, it's not exactly the precise definition, but if we really want the precise, would be this is going to be for every epsilon greater than 0. There exists an n in z plus such that for every m and n greater than equal to n, we have that this horrible thing, this symbol f of x, y, dA minus the sum from I equals 1 to n and the sum from j equals 1 to m of f of x I star y j star dA less than epsilon. So we can squeeze it eventually and get it closer and closer to being exactly this volume that we're looking for. Don't worry, we're going to get a better way using iterated integrals in the fundamental theorem of calculus. We're not going to use the definition here to compute double integrals. Don't worry. That's not the goal. So if f of x, y is a positive valued function, the surface is above in the positive orthanc, or it's in the positive octant, then what we can do is compute this as volume if you want to take the absolute value of the multi-valued function, we can eventually. But essentially what this is saying is, as long as it's a positive value function, then we can interpret this as volume the same way as if we have a positive function f of x, we can compute this as the area under f of x, the graph of f of x, and above the x-axis. So if we have this, then the volume under the graph of f of x, technically above the rectangle AB cross CD, is the double integral so the volume of that solid region S is going to be equal to the double integral over the rectangle of f of x dA. So just like the definite integral can be computed as the area, of a rectangle R is equal to the single integral over the integral of f of x dx. It's the complete analog. So this is area, this is volume. There's cats everywhere, but they won't come in here just to harass. And you can guess when we do this, we're going to spend a lot of time with the double integral now. But you can guess at the fact that the triple integral will be defined the exact same way. When we do the triple integral, we're going to get a cube. And then we're going to chop the cube up 3 ways. Like this, chop, 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 chop. And then once we do that, and then we can do triple integrals over solid boxes and then general solid regions in space. All right. Iterated integrals and computing double integrals. And Fubini's theorem. Fubini's theorem is Fubini is the first guy that shows that we can actually do this. So we want to use partial integration to compute double integrals. What do we mean by this? In other words, we hold one variable constant. It doesn't matter which one, but I'll start out with variable y. So we hold y as a constant. Let's do x as a constant. It doesn't matter, but they're going to hold classically x as the constant first. And integrate the other variable, y. So what we're going to do do with this, what we mean by this is, say I'm going to have a function which is entirely an integral a of x, because this will be the integral from c to d of f of x, y, dy. Why is that? As an example, suppose I'm trying to compute why is it a function of a entirely. Because if I have the integral, say, from 0 to 1 c to d of x squared plus y squared dy, what I'm doing is I'm holding x constant, so x is just a number. So the antiderivative of this is equal to what? This is going to be x squared y. X was just a constant, so I'm taking the antiderivative of this, and then plus 1/3 y cubed, evaluated from 0 to 1. But now this is going to be what? X squared plus 1/3 minus 0. But this is now, you can see why at first it's hard to see here when we do the theory, why I can say that this is just a function of x. But once I actually hold x as a constant, integrate y, then what we're going to get is just a function of x. And then when we have a double integral, over a rectangle, we can compute as follows. What are we going to do? We're going to have an integral from a to b, and the integral from c to d of f of x, y, d, y dx. What we're really doing is we're saying that we're going to compute this integral first, and that is exactly equal to now the integral from a to b of a function just of a of x dx, which will be equal to the antiderivative of a evaluated from a to b. So because we're going to do this business of iterated integrals, or do one integral inside and then do the outside, because we're just going to hold this partial derivative, is partial integration technique is the trick. We're just going to hold one of the variables constant and integrate the other variable, and then we get a function of just x in this case, and then we can integrate that function of just x from a to b. Now we just have a regular, this is just a regular definite integral. And this is a definite integral, where I'm holding x constant. So this is the idea of how we're going to compute iterated integrals. So let's try this. And does the order matter? Can we switch the order? This will be Fubini's theorem. Does the order of integration matter? In general, yes, it will. Bring on. You being mad? That's Kitty. the young one, she's chasing everybody else. The old ones, they were just telling her to go away. For over rectangles, no, it doesn't. Let's do an example. So what we're asking is this. And notice that what we're saying is, are we integrating this one first or last? So are we doing integration with respect to y first and then x, or are we doing integration with respect to x first and then y? That's what we're asking. And over rectangles, this is what Fubini's theorem says. Fubini's theorem says no, it doesn't matter. It doesn't matter if it's a rectangle. If it's not a rectangle, it's general areas in the plane, then it does matter. You have to redraw, or you're not going to like me when I give you these questions. But let's do an example. Where's this one? I want it. Compute the volume of the solid S below the surface, which is just a plane. The battery's dying in the pen. Which plane is this? Z equals 4 minus x minus y. And above the rectangle, which is going to be zero 2 cross 0 1. I'm going to do it two ways just to show you. So one, so we're going to integrate y first, then integrate x over this rectangle. This is important. It doesn't work in general, but over a rectangle it will. So the volume is going to be equal to the integral from 0 to 2, the integral from 0 to 1 of my surface is 4 minus x minus y dy dx. Notice that I'm integrating y first, then x. So when I do that, this is partial integration, or I'm integrating with respect to y, I'm holding x as a constant. So this becomes the integral from 0 to 2 of, now what do I have inside there? I have 4 minus x times y minus 1/2 y squared, evaluated from 0 to 1 dx. And now that I put the y's in, the y values in there, the constants, all the y values will disappear, and I'll have a function of just x. This is equal to the integral from 0 to 2 of now 4 minus x minus 1/2 times 1 minus 0 dx. So what do I get? I get 4 minus 1/2, or this is the integral from 0 to 2 of 7 over 2 minus x dx. This is the a of x that they're talking about. Now that I have a function of just x, I can integrate with respect to x. Now I integrate with respect to x. This will become 7 over 2x minus 1/2 x squared, evaluated from 0 to 2. So what are we going to get? We're going to get 7 over 2 times 2 minus 1/2 times 4 minus 0. And so we're going to get 7 minus 2, which is 5. Did that matter? Let's do it again. How much time do we have? We have lots of time. Now what happens? Let's do integrate x first, then y, over a rectangle. Remember, always, this is going to be the integral from 0 to 1, the integral from 0 to 2 of 4 minus x minus y dx dy. This is going to equal, by holding one constant, remember, x first. So now I'm holding y constant. So now this becomes the integral from 0 to 1 of, let's just write that differently. Why did I do that? I did that so that I can do, this is going to be 4 minus y times x minus 1/2 x squared. Now evaluated from 0 to 2 dy. Once I put that in there, I'll get a function of just y instead of just x. This is the integral from 0 to 1 of 8 minus 2y minus 1/2 times 4 minus 0 dy, which is going to equal the integral from 0 to 1 of 6 minus 2y dy. Now what are we going to get? This is just, notice that this is just function a of y. Now I can integrate with respect to y. That gives me the integral, 6y minus y squared, evaluated from 0 to 1, which is 6 times 1 minus 1 squared, which is 6 minus 1, which is 5, which was the volume. So the volume is 5. And it equals the integral the other direction. 5 equals that volume. So once they start noticing this, that the order doesn't matter over the rectangle, this becomes Fubini's theorem. Which says exactly this. You can integrate if you have a rectangle. If f of x is continuous, it's supposed to say continuous over the rectangle R, which is AB cross CD. Then the double integral can be computed as that volume, or it could be negative or 0 if you don't make sure that your surface is positive. But that double integral symbol is equal to both iterated integrals, the integral from a to b, the integral from c to d, f of xy dy dx, which is also integral from C to D, the integral from A to B, f of xy dx dy. So the order doesn't matter over rectangles. The order of integration can be flipped or doesn't matter. Over rectangles. Over general regions, it will matter. So you can't, once we get more complicated curves that aren't just straight lines, you can't just flip the integration and be like, oh, it's the same. It doesn't work out that way. So yeah. Let's do a couple more examples. Do we have any specific ones I wanted to do? I have applications there. One. Yeah, let's do this. Integral. Let's put it this way. Where R is the rectangle. And then the second one I can do, I don't know if I'll have time for both. And then let me make for the first one, what's that one, x. I like to do that to show you where to put all the pieces in this horrible new symbol and machinery that we got. And then in the second one, let's do the integral over a rectangle of xy dA, where the rectangle is equal to 0, 1 cross 0, 2, and f of xy is some kind of ellipsoid. So there's some more iterated integrals. What it's going to also show is, I'll try to keep it fairly tame. Right now it's just polynomials, etc. But you're going to have to know integration techniques, partial fraction decomposition, integration by parts, trigonometric integrals, trigonometric substitution. These types of things may crop up when we do integration. I can go over this maybe next week. Today I just wanted to make sure that we had the definite integral and Riemann sums reminder. Then double integral machinery is mimicking this, and then how to at least compute iterated integrals. Next week I'll start double integrals over general regions, and then when we talk about that, we'll start doing applications as well. But for now, we just want to be able to compute efficiently double integrals over rectangles. The way to do that is with a bunch of examples, and know that it doesn't matter. I start with y first, then x, because those are the books that I usually started with. And then if I just keep it when it gets more complicated and we have to do polar regions and all of these things first, or it gets more and more complicated. So I try to stick to my guns and make this as simple as I can. When I'm doing it, I want to do integral of y first and then x. If I have to change it, then this will get good at changing the variables when we have more general regions. But sometimes it will force you to, because the antiderivative will be so complicated that I don't expect you to know how to do that horrible antiderivative. I want you to instead change the order of integration, and then you'll be able to integrate much easier. It's hard to explain what that means, but the moral of the story is doing double and triple integrals isn't going to make life better. You need to know the formulas and antiderivatives of a bunch of functions, including arc, tangent, and all of these guys, etc. substitution rule, integration by parts, partial fraction decomposition. It never ends. For the first few, I'll keep the integration relatively easy so you can see what's happening with the machinery of iterated integrals. So the integral over this rectangle of x squared y dA is equal to, by Fubini's, it doesn't matter. So I'm going to do it, stick to my guns. The integral from 0 to 3, the integral from 1 to 2. Notice where this came from. 0 to 3, 0 to 3. 1 to 2 is the y. So this was y, and this was x. Of x squared y, and then dy dx. So when it's Fubini's and it's a rectangle, if I have the choice, I just by mantra just do dy first, and then I'll do dx. This is equal to the integral from 0 to 3 of, I'm holding x constant, I'm integrating y, so this is x squared 1/2 y squared, evaluated from 1 to 2 dx. This looks like it wasn't the smartest way to do this, because integrating the x1 would have gave me a little bit easier, because it would have been 0 to 3 first, but we would have to do it either way, calculating at 1. So we have the integral from 0 to 3 of, now what do we have? X squared over 2 times 2 squared minus x squared over 2 times 1 squared dx. That's using the fundamental theorem of calculus on the y values. Just in case, the 2 is going there, and the 1 is coming from there. F of b minus f of a. Now this is equal to the integral from 0 to 3 of, what did I get? 2x squared minus, okay, so it's x squared minus x squared, so I have 3 over 2x squared. X, just a function of x. Now what is this going to be? This is going to equal 3 over 2 times 1/3 x cubed, evaluated from 0 to 3, which is going to be equal to what? This will cancel. I have 1/2 times 3 cubed minus 0 cubed, which is 27 over 2. If you want, as an exercise, you can compute that the other way. Oh, it should be 1 to 2. Still equals 27 over 2, but you should practice computing the other direction to show that Fubini's theorem is working. For the second one, I have the double integral over the rectangle of 10 plus x squared plus 3y squared. Was that right? Yes. dA is equal to the integral from 0 to 1. What was my rectangle? 0, 1, 0, 2. 0, 1, 0, 2 of 10 plus x squared plus 3y squared dy dx. So this is equal to the integral from 0 to 1. I'm holding x constant first, and I'm integrating with respect to y. That's going to give me 10 plus x squared y plus y cubed, evaluated from 0 to 2 for dx. Now I put the values in there. That equals the integral from 0 to 1 of 10 plus x squared times 2 plus 2 cubed minus 10 plus x squared times 0 plus 0 cubed dx. This is just 0, obviously. So what do I get? This is equal to the integral from 0 to 1 of, I have 28 plus 2x squared, it looks like, dx. Just some horrible number. So what are we going to get? This is going to be equal to 28x plus 2 over 3x cubed, evaluated from 0 to 1, which is going to be equal to 28 plus 2/3. We're going to multiply by 3. Get some number, which is the area. Again, if you want, you can try exercise, use Fubini's theorem to flip that around, and you can get the same number either way. But I think that's good enough for now. For the first class, I guess now it's welcome to 215. This is multivariable calculus. We're going to start off with double and triple integrals and applications of double and triple integrals. So applications will be mass of objects in the plane, center of mass of objects in the plane, or planar lamina, and then we can do eventually charge density in the plane and stuff like this, and then density and center of mass and all this in 3 dimensions, centroids. And then we can do charge density of the sun. We can now look at a spherical object that's in 3 space and look at the charge density of that object, etc., etc. So this will be the start, and then we'll get into vector calculus and Green's theorem, Stokes' theorem, divergence theorem towards the end of the class. If you have any questions, I will this weekend. Now that we're actually going, I will probably make assignment 1 just not for marks. It's still the ODEs one. I don't want to change the order or anything, but we'll probably start out with assignment 2, which will be double and triple integrals, and then we'll go from there. But I'll tweak it slightly and then send you an email at some point this weekend. So have a good weekend. I'll see you on Tuesday.